Hello and welcome to Bay College's Intermediate Algebra Online Lectures. My name is Jim Comer. Today we're going to look at section 8.3 that deals with exponential functions. But before we look into this, let's look at an example. We're going to go over to this board here, and my example is, let's say Bill Gates offers you a job, and you only have to work for 30 days, every day for 30 days. And the first option of your pay is $10 million. He's going to pay you $10 million in order for you to work for 30 days. Sounds like a great deal, right? But he gives you a second option for your pay. The second option, he says, well, I'll pay you using an exponential function, where I'll pay you 2 cents on the very first day, and I'll double it every day after that you work for me. Well, if you think about it, if I am working for 2 cents on the first day, I get 4 cents on the second day, and 8 cents on the third day, and 16 cents on the fourth day, and 32 cents on the fifth day. Well, I've worked 5 days, and I've only earned 62 cents. It doesn't sound like much. But what we have here is the actual model of that equation. So let's jump all the way to the end. What am I going to get paid on the very last day? Well, that would be day 30. I'm working 30 days. And if we evaluate this function, because we're familiar with function notation, if I put in 30 for here, I put in 30 for there, 30 minus 1 is 29. So I have 0.02 times 2 to the 29th power. Well, 2 to the 29th power is a very huge number. And if I multiply by 0.02, I don't know the exact figure, but it's about 10.7 million. Now let's assess. If I took the first option of 10 million, on the last day alone of the second option, I get over 10 million. Well, the day before, using this function, I got over 5 million. The day before that, I got over 2.5 million. If you sum up the pay that you received on each day using this function, you would have been paid over $21 million. Exponential functions grow exponentially, really fast. So now we're going to go over here and look, why is that? Why do these functions behave that way? Well, if we look, this is our standard form of an exponential function. And we're just going to do a little definition here. Obviously, we know function notation. This here is called the base. And if we're familiar with exponents, and hopefully our background in exponents is really strong, if not, we might want to go back and review it before we start this concept. This is our base. This is what is being multiplied by itself X amount of times. And this, of course, is our variable. And I'll just abbreviate here, variable. Now, when it comes to exponential functions, our base has to be greater than 0, because negative bases don't apply to functions here. And our base can't equal 1. Well, why not? Well, 1 to any power is still 1, so it really wouldn't change. It'd be a constant function. It wouldn't be exponential. So base larger than 0, but not equal to 1. So that's our definition. This is our base. And that's an important concept, because when we look at these, it's the base that we're multiplying by itself. You know, the variable is just how many times we're going to do that. So we're asked to graph f of x equals 2 to the x. So our exponent is our variable, and that is an exponential function. So let's graph it by plotting some points. If I put -3 into here, 2 to the -3rd power, and this is why I said it's important to know your rules of exponents. Negative exponents are reciprocal, so it's 1 over 2 to the 3rd power, or 1/8. If we plug in this value, -2, we get 1/4. -1, well, 2 to the -1 is the reciprocal of 2, which is 1/2. 2 to the 0 power, if we plug that in, well, anything to the 0 power is 1. And then 2 to the 1st, 2 to the 2nd, 2 to the 3rd power. If we were to plot these on a graph, let's go over here and plot them. We have these fractions. We have 1/8. We have 1/4. We have 1/2. And then at 0 we had 1. At 1 we had 2. At 2 we had 4. Up here. And at 3 we had 8. A value way up here. Right? Now let's just graph this and take a look. This is the behavior of an exponential function. Notice as our x's, our variables get larger, this thing starts increasing extremely fast. It goes way up high. So this is our exponential function. So let's look at some other exponential functions and look at their behavior. Now what we have here is a graph of f of x equals 3 to the x, where our base is 3, g of x is 4 to the x power, h of x is 5 to the x power, so we have different bases. And if we look at these, the one with the larger base, as it gets positive, it grows much faster. It's going up there. As soon as, in this case, x is 2, we're already up to 25, which is off our graph. So this is just an example of, this is called exponential growth. Now the thing about exponential functions is they have certain behavior. And notice it doesn't matter which one, what our base is, they have the same behavior. They're all increasing as we move from left to right. Well, what values of x can I put in here? Let's define the domain. Well, the domain is all real numbers. And I like to use that symbol, which means all real numbers, or you could use interval notation from negative infinity to infinity. Well, let's assess the range, our y values. Well, our y values, as this line comes down, as it goes to the negative direction, it gets closer and closer to 0, but it never actually becomes 0. Maybe it's 1/5 or 1/25 or 1/125. It gets smaller and smaller, but never equal to 0. So it just approaches. So what's our range? Well, it's never equal to 0, but we can see these arrows continue on to infinity. So our range is 0, not including 0, so we use a parenthesis all the way to positive infinity. Well, let's look at our y-intercept, this point right here, and we notice, hey, they all share that same point. When x is 0, y is 1 in each and every one of these, and that's one of our fundamental rules of exponents. Anything to the 0 power is 1. So they all have the same y-intercept of 0, 1. Now let's look at the x-intercept. Well, if it never is equal to 0, it only approaches it, then it doesn't cross this axis, the x-axis. So there is no x-intercept. So our x-intercept is none. There isn't one. Now, if we take a look at this, that behavior holds true, but let's look at these. These are also exponential functions, but these are decreasing exponential functions. These were increasing, these are decreasing as we move left to right. The first function, f of x, this one right here, is 1/3 to the x power. G of x is 1/4 to the x power, and h of x is 1/5 to the x power. H of x, g of x, f of x, respectively. Well, if we look at their behavior, their domain, well, I can plug in any value of x. It doesn't make it undefined or not real. So our domain is all real, just like it was with an increasing exponential. Our range, well, as it gets closer and closer to infinity in the x, it gets closer and closer to 0. Well, let's think about that. 1/3 squared would be 1/9, or to the third power would be 1/27, or to the fourth power would be 1/81. Notice the denominator is getting bigger and bigger and bigger, so it's getting smaller and smaller, but it will never equal 0, so it will get closer to 0. Kind of the opposite of this, right? So our range, because it never is equal to 0, 0 is our limit, our lowest part. But if we look at this way, in the negative direction, these are actually continuing on to infinity. So our range is to infinity. Our y-intercept, well, if we look at this, again, they share that same y-intercept. When x is 0, we get 1 because anything to the 0 power is equal to 1. So our y-intercept, again, is 0, 1. And our x-intercept, well, if it never is equal to 0, it never crosses that axis. So again, there is no x-intercept. But as we had learned with, parabolas, we can have transformations or shifts left, right, up, down. So there could at some point be an x-intercept, but there would have to be some sort of horizontal shift here. Well, let's look at an example that has a shift to it, but it's not necessarily a vertical shift, it's a horizontal shift in this case. Notice x minus 1. If we were to plot some points, well, let's do that. Let's go ahead and plot some points. Let's choose a negative value. Let's say -1. So if this is -1, 3 to the negative 1 minus 1. Well, negative 1 minus 1 is negative 2. 3 to the negative second is 1/9. So a very small value. And then 3 to the, let's say, the 0, right? 0 minus 1 is negative 1. So when we're 0, we have this point right here. And I'm going to label this point 0, 1/3. Because that's an important point, right? It's on our y-axis. And now I'm going to put in the value 1. 1 minus 1 is 0. 3 to the 0 power, well, anything in 0 power is 1. So when I put in 1, I get 1. Okay? And let's try 2. 2 minus 1 is going to give me 1. 3 to the first power is 3. So we have a value somewhere up here. And we can see that same behavior because it is an exponential function. Our variable is in the exponent, this x right here. So we can see that behavior there. So let's look at this and assess the domain and range. Well, what values of x can I plug in there? Well, the domain hasn't changed. I can plug in anything. What's my range? Well, my range, it still approaches 0 as we go in the negative direction, but it never becomes it, so it's 0. And as we go to the right, that arrow heads up, up, and away off to infinity land, right? Let's look at the y-intercept. Now, because this is a horizontal shift, it pushed the graph to the right, right? Always the opposite direction of what we see here, like we did when we had h's and k's in our parabola, right? So now our intercept is actually 0, 1/3 for our y-intercept. But our x-intercept is non-existent because this never goes to the x-axis. So we can see that same behavior. Our domain and range hasn't changed, but our y-intercept has. Now, our domain and range can also change if we had that vertical shift. If there was a value out here, maybe I say -2. Well, that would take the graph and bring it down 2 units for every point. So that is essentially the basis of exponential functions. They're either exponentially growing or exponentially decaying, like we see here. And the other thing is, we have to be able to identify the domain range, y-intercepts. So let's move on to an application problem. One type of base that we see very often in the maths and the sciences and even in business, you'll see this right here, it's E. This is the letter E, and it's used to represent an irrational number. That irrational number is 2.7182818284590, and it continues on. It's irrational. It's non-repeating, non-terminating decimal. Now this is what we call the natural number because it appears in nature. We find it in many different places where we try to quantify some of our measures. Now, one application to it is compound interest versus continuously compounded interest. Now maybe you've seen this formula before, but we'll define it anyways. One application to exponential equations is compound interest. Notice we have some variables in the exponent. That's defining an exponential equation. Where A is the amount that we end up with after some time t if we invest P money. So this is our principal, this is the amount we're going to get out. R stands for the rate. What's our interest rate? If I say 6%, I know that's 0.06. I know how to convert percents to decimals. N is the number of compoundings. As an example, if you're told, well, I'm getting an interest rate of so much, but it's compounded quarterly. That means 4 times a year we find the interest and we add it to the account. So we should be somewhat familiar with compounding quarterly, semi-annually, or biannually. They mean the same, or whatever. We should be familiar with that terminology. All right, and of course T stands for time. So let's look at an example. We're asked to find the amount of money if we invest $100 at 2.5%. 2.5% is 0.025. It's going to be compounded semi-annually, which means twice a year, so my N is 2. We want to find out how much money are we going to have after 10 years. So we're given this information. This is the only thing we need. Essentially, this example just says put it into a calculator. This is an example where we would use a calculator because it's not really a pretty number when you plug it in. All right, but let's actually put it into an equation so you can kind of see. We're taking $100 and we're going to invest it at 2.5% compounded semi-annually, twice a year. So, for 10 years. Now what this is telling me, if you think about it, I can add this together because it's in parentheses using order of operation, but I'm going to raise it to the 20th power, which is going, which is essentially, I would say, isn't math you can do in your head. I know I can't do it in my head, but I can plug it into a calculator. I can find these values. This in here is going to be 1.0125 and raise that to the 20th power, and then multiply it by 100, essentially move the decimal 2 spots. And we'll have an answer, and because I already calculated it out, it's approximately $128.20. So now if we had just assessed what we found, putting $100 into an account for 10 years, compounded semi-annually at 2.5%, we're going to end up at the end of that 10 years with $128.20, essentially $28.20 in interest. So that doesn't seem so bad, right? Compounded semi-annually. But when it comes to compounded interest, well, what if it was compounded monthly? Well, that would be 12. What if it was compounded daily, 365 times in a year? Or what if it was compounded every second? Well, that's where this number comes into play, our natural number. As n goes to infinity, becomes really, really, really big, essentially this fraction, as the denominator gets bigger, this gets smaller. So this is getting closer to 0, but it's never 0. So I have 1 plus almost 0 as n goes to infinity. But then I'm going to raise it to a really big number times t. If this number is going to infinity, this becomes 0, this becomes infinity. So what's 1 to the infinite power? Well, that would just be 1. 1 to any power is 1. That's why our base can't be equal to 1. But because this is getting large and this is getting close to 0, but it's not quite 0, if you actually calculated this out, it actually becomes this number. It just appears in nature. So we have to understand that number. So what happens when we take a limit, and honestly, to do a proof on this, we have to use some calculus, but it becomes this equation right here. And this is the continuously compounded interest equation. A equals P e to the RT. So P, our principal, still the same variable, times E, the natural number, but it's the natural number that's raised to the rate times the time that it's in there. So let's look at this example. We're told to find how much money we have if I invest $100 at a 2% interest rate for 5 years. Well, if we plug that in, we're going to say, okay, how much money do I have if I invest $100 E raised to the 0.02 times 5. So E to essentially the 0.1 power. Now, if you calculate this out, let's see, what $110.52. Now, plugging this into your calculator, one of the requirements for this course is to have, at minimum, a scientific calculator. And if you look at your calculator, you should have a button that has this on it. Or maybe your button shows this on it. So maybe you have a shift key and you have to access that. But any graphing calculator will have this. In the next section, we'll actually look at the function of that. We've talked about inverses in the previous section. These are inverse functions. So you should find that key on your calculator, be familiar with it, and know how to use it for equations like this. And you'll see them in some of the homework assignments. So that is an introduction to exponential functions. Thank you for watching.